So I'll talk about spatial AI in particular. What I mean by this is essentially having methods that help us understand the world from sensors to assist people and enable robots to interact with the world. And so essentially we're thinking of all these type of devices, and then we need essentially for doing this, we need geometry, semantics, and also affordances in the world to be able to interact with it. This is actually our latest robot that we got. It turns out it's actually the first external Ricci 2 that was available. I'll start with a little video here that shows a little bit the type of digital twins, at some level, the type of digital twins that we're looking for. It's and kind of how you could use those. And I hope the sound is going to be there. I guess it's not very loud there for the projector. Anyways, you kind of see essentially this kind of copilot in the loop here, but you have a digital twin that has kind of represents the real space and the physical. So the physical space is kind of closely aligned to the digital space. You have of all the kind of functional elements, you have a digital representation. All of this is not only single elements, but they're all in the same large space. As you walk around, you can access the relevant digital information of kind of any device. Okay, so let me skip that. So essentially, first thing we need to do for that is actually to be able to build a kind of map of the environment so that we can always be localized. Here you see just a visual digital twin on the right of our offices or former offices for Microsoft. And then as Avi is walking around and looking around, you kind of see that all being mimicked in the digital twin kind of on the right there, right? And you see her view, egocentric view there. And so as we know exactly on the digital side what she's looking at, we can essentially provide the exact relevant pixel aligned kind of relevant information to it. To enable that, we built multi-device mapping and localization system. So it works as follows: as a person walks, just to generate these kind of AR experiences, the device itself is running a SLAM system, a VIO and a SLAM system, and it's kind of building up a map as you see there. What we do is we transfer that from the device to the cloud, at least part of the information enough to kind of build a kind of landmark-based 3D representation. As multiple agents are mapping at the same time or at different times, eventually those maps are localized with respect to each other and can be merged into a single representation of the world. This is, of course, important that you can bootstrap a representation by just walking around, and then merge all the information in and share that, and later have other people access that and reuse that. And so you can actually build up your digital twin and attach information to these maps and do that. You also see here, it's not only the sparse scene point, but actually also has radio signals that help with localization, but also surfaces to which you can attach all the information or label information. Now here's just that a bit more at scale. This was a few hours of walking around simply with the HoloLens device through one of the Microsoft buildings on the Microsoft campus in Redmond. And you see we essentially reconstructed like a full reconstruction, including all the furniture and everything that happened to be there when I worked for it. Okay, and here's the same kind of in a industrial setting. If you want to do this on the academic side, we've also been working a lot on Colmap. Johannes started this in 2016, but the project is still ongoing. For example, for rigs, so if you have more than one camera, you have a device with multiple cameras. We now natively support rigs. So this can be vehicles, or this can be head-mounted displays or devices or so with multiple sensors that all move together through the environment. Then we natively support this now in Colmap, for example. We've also Colmap has a challenge that it can be quite slow if you want to do really large spaces. So Glomap is an alternative that essentially works pretty much same quality. But it's much faster in many situations. In particular, instead of Glomap being a sequential kind of, add a few images, optimize, add images, optimize, add images, optimize, kind of builds up from some place, starts building up a map of the whole space. Glomap is actually looking at everything at once. It's first figuring out the relative rotations between all the cameras. This is called rotation averaging. And then, so after you've actually built up the whole scene graph, so figured out all the pairwise epipolar geometries, we figure out the relative rotations of everything. Once the relative rotations are figured out, the rest, recovering the 3D locations of points, of landmarks, and recovering the 3D locations of cameras is a much simpler problem. You could write it linearly. We use a bilinear formulation and essentially optimize that from random initialization and get really good results. So here you see a few of those ongoing. So you both see the kind of single scene kind of models, like here's some of the ETH3D and other data sets. But then you also see really large urban kind of, this is a whole district of Zurich, many streets and so on. So really something that is still way outside of what, methods like VGGT and others can do. They can do these three typically, but they cannot at all solve these kind of problems because there's just too much, it's too large of a graph where, with 24 kind of steps of iterations, for example, there's no way you can actually solve that problem because there's many hubs in the viewing graph of one street to the next street to the next block to the next block to, it's a very long chain that you need to propagate. These one-off feed-forward transformers have no way to cope with that, for example, right? So these methods are still very much required. Then, of course, we also do a number of feed-forward things if we want to get visual representations. Here's some recent work on essentially immediately going feed-forward from a few images to a Gaussian splatting representation. And essentially, it uses two different kind of ways to extract information. One is a multi-view transformer, think of VGT or things like that, that essentially also have a cost volume and generate. Actually, this one is still using known cameras. So we, on the one hand, do multi-view stereo, but on the other hand, we also do monocular kind of inference, merge all of that together, optimize that towards minimizing the viewing loss. And so therefore, this can all be unsupervised, pre-trained. Again, this is how it looks like. So just from a few pictures, you can then generate a virtual visit through an apartment and have essentially a Gaussian splatting representation. Then here's kind of a follow-up on that, which was immediately also estimating the pose at the same time. Here's a few examples of that in action. So the first and the last view were input. The rest of the video was generated through our network. And of course, these were not in a training set. Okay, and our latest work that actually will be presented in the next few days here at ICCV. And this is a collaboration with Meta. So my PhD student, Tobias Fischer, has been driving this work. The idea is to do first a sparse reconstruction with few views. This is a not perfect reconstruction, but then by building in kind of leveraging the priors that are built in flow models, diffusion models, we can actually generate from the sparse information we get for the not perfect information from the initial reconstruction from the sparse set of views, we essentially generate additional views, right? So we leverage the knowledge of how images look like to essentially complete the intermediate images, so additional viewpoints to allow us then from those to do a better reconstruction. Okay, so we found a way, this is essentially finding a way to leverage what is baked in the 2D foundation models, like diffusion models, to essentially leverage that kind of knowledge of how a scene looks like that's baked in there, to leverage that to bring it to 3D essentially, into 3D reconstruction. Then to do many of those things, it's important to actually be able to measure how well you're doing. Of course, we've done things like ETH3D and so on. Our latest efforts in this space are, on the one hand, this Lamar dataset, which is very large scale capture on this multiple of these environments, with essentially also ground truth alignment to ground truth data collected with LiDAR, et cetera, et cetera. And so we have this both for handheld devices and for wearables. Our latest effort, which is actually also going to be published here, is scaling up the trajectories from single building or a small part of a neighborhood. Essentially, if we look, let me get the cursor here. There's a cursor. Okay, here's the cursor. So if we essentially, the neighborhood that we had before was a few streets down here. Now we've essentially captured long sequences working with ARIA glasses all the way through Zurich. And to then get kind of ground truth level quality centimeter accurate registrations, we essentially leverage the survey, the ground control survey points that are actually spread all over the city. We've remeasured some of them to make sure they meet the accuracy. And then we put QR codes on top of QR codes like this here, or control codes on top of it like this. So we center that on the point. So there's a little hole in the middle. We center it on the point. And then in the glasses, we can accurately compute this location and correlate it to the ground truth location. And so that way, along the trajectory, we have a lot of control points. Anyway, so this is a way to also get really validate VIO at scale and on really large scale, and also having challenges like trams and low light and exposure changes and many things like that as you go from inside to outside, et cetera, et cetera. Another effort is to do this cross-device, to really focus on cross-device alignment. Here you see essentially from capturing with a kind of high-quality LiDAR-based kind of sensor together with also robots, sensor data, with wearables, and with tablets, etc. And so we have a challenge. Actually, this afternoon, there's a workshop on this, and the paper itself was at CVPR, that essentially validates all the cross-device alignment. It's much harder to validate, to match cross devices because the camera sensors are different, but also because the viewpoints are different. Often, the spot will be down here somewhere, and then a wearable is here, the handheld device is here, wearable is here, and then if you have a drone, it's flying somewhere, right? So there are challenges in doing this. So this is all to be able to kind of build and assemble the initial geometry of those things. But then beyond that, and Tom is just here. So this was a collaboration with Google. And driven by Sungyu Peng, back then my PhD student. And so here we wanted to add layers of semantics on top of the geometry. And so the idea was to again leverage 2D foundation models here that essentially clip that was aligning text and have a text encoder and an image encoder, and extend that through distillation to on kind of the Matterport kind of indoor data set, to extend that to also be able to extract the aligned embeddings directly from the 3D point clouds. And so if you do that, you can now, from when you get a 3D point cloud, you can, for every point in there, you can both from the image data, the texture images, as well as from the 3D point clouds, you can extract embeddings. And then when you get a query, as we'll see here in the video, so if you enter a text query, you can pass that through the blue encoder network, you get an embedding, and you correlate it to all the points in the scene, right? That have been have their pre-computed embeddings, and you get essentially the strongest response based on what you enter. So this is open vocabulary. You can ask anything. So you can ask about objects, but you can also go beyond that and ask about and so this is still objects here, but you can also ask about affordances. You can ask about, where can I sit? I think that's coming soon. We're still in the objects here. You can ask about materials. You can ask about anything that's been captured by those foundation models, is essentially something you can query for. Okay, so this becomes quite useful in many things. We've then, so here's the material, for example. Okay. So we've also extended that to going to objects. So immediately work on object instances. So this was the Open Mass 3D Lord. Also collaboration with Google, but Google in Zurich now, between ETH and Google. And so essentially we had object instances, and then for every object, we essentially determined from the imagery what the likely kind of, also clip embeddings, and could essentially query objects. We realized that so the instance segmentation was actually still a not fully open vocabulary. So then we went to leverage SAM. So again, a 2D foundation model, and try to lift it to 3D. So segment anything to essentially bring it to a more 3D kind of segmentation method to lift it to that, and enable queries of objects of kind of arbitrary sizes and stuff like that. So as you see here, where Mass 3D often was failing to get the right object, but then Segment 3D here, we could actually hone in on the right size of objects. So by leveraging what Segment Anything was doing. And our latest work, which is going to show up here in this area of finding kind of extracting semantic information from images, is 3D mood. So molecular open set object detection. So that's what mood stands for. And so here, essentially, you can, by looking at an image and providing a kind of a query, it will look and find those objects in the scene and essentially extract a kind of three-dimensional bounding box for each. So identify a three-dimensional bounding box for all of the objects that you ask about. So in that sense, it's open vocabulary kind of 3D instance detection into the images. Okay, so that's good. That's all about finding the semantics in the scene, but really we need beyond that kind of understand what people are doing in the scene. So not only what the objects are, but actually what are the activities, what are people doing, and also in a way that we can later transfer that potentially to robots or other things and understand also affordances. So here's our early work in the space was, detecting like what the hand was, so the hand motion and the object motion, as well as the kind of activity that was going on. With applications like this one here, this was some work we did at Microsoft, where wearing the HoloLens, you would do a certain activity. One of the applications of HoloLens was to do an activity that would allow you to, that would essentially guide you through an activity. So it would tell you step by step what to do. But the problem was with what we had in HoloLens, it was actually only telling you step by step what to do. It had no way to check if you were actually carrying out those steps. Okay. So here we actually automatically follow along the different steps in a procedure. And then if the person would make a mistake, for example, like in this video, they open it, but then instead of taking the old cartridge out, they already grabbed a new cartridge. And of course, that's not going to work. So essentially we can intervene and we can tell them that they did the wrong thing and they should correct and so on, right? So that's the kind of applications with in mind. Then we then went further there to the Holo Assist project, which was published 2 years ago at ICCV, where you had the scenario, which in the end, the most used scenario for HoloLens or for this type of technology was really a remote assistance scenario. So it's a remote person teaching an on-site person how to do it. So meaning that you can decouple the kind of the person, doing the task from the person with the expertise. You don't have to have the person with expertise on site, so that this is very flexible. If a machine breaks down, you can call up the people that know about the machine and just have a general technician on site kind of resolve the problem, right? So we wanted to kind of leverage that same scenario, but now in a way where we could really learn and eventually get to kind of a co-pilot that would assist you in these type of tasks. And so the first step in that was collecting data, where we had a remote person explain to the local person what they were supposed to do. We had a number of standardized tasks, and then people had to kind of carry out those tasks, but the person on site didn't know what they were supposed to do. All the instructions were transmitted from the remote person, with the idea that we would really capture what it takes to kind of transfer the information and have a person with a general knowledge kind of carry out those tasks. The interesting thing was different levels of expertise. Some people already were familiar with the objects that had to be kind of manipulated or done something with. So those people would, very high level instructions would suffice. And then some other people were confused by the object, didn't know where the battery compartment was or this or that. So you had to explain them much more carefully. And so by capturing this over multiple individuals, we are essentially capturing different levels of description of the tasks, kind of in an automatic kind of way. Okay, so here's some of the data we collected. This was all multimodal data, so it's both RGB data. We use the hand tracking that's built in HoloLens to know where the hands were. We use the eye gaze, the eye tracking to know where the person was looking and paying attention to. We had the depth camera from the HoloLens. So all of this was captured. We, of course, had the full audio back and forth. And then we, on top of that, had people annotate these. So we had a company annotate all the activities, the fine-grained activities that were taking place, and also annotate when mistakes happened, when corrections were made, when people had to do that. So all of this was annotated. We have about 200 hours of video of these activities with, many hundreds of different tasks being carried out. And so that data set is available for people to use. More recently, we've also done a collaboration with EPFL. And so here we collected a Ego-Exo data set, where we essentially have, as you see up here, you see there you see the Ego viewpoint, and then we have 9 exo viewpoints, actually all with depth cameras and Kinect. And then we essentially have the eye gaze, the hand tracks, we have the full body pose. We even have some of the tools instrumented. So we have the IMU and the knife. So if you're chopping, we actually really know exactly what you're doing when you chop. So things like this. So there's a very rich data set, kind of exo data set for kitchen activity. We have tens of subjects doing 5 recipes. So it's 5, they all do the same recipe. So it's very scripted. They do it in different ways, but they all carry out the same recipes, the same 5 recipes. So it's actually a quite rich data set. Okay. We've also done some work on having large video models that multimodal video models, multitask video models that can, where we've used many data sets where we have eye tracking available, and we learn to predict from cross modalities. So we do like transfer between modalities. And so this is also a paper here by Jen Lee, and it's mostly from the lab of Siu Tang, who's a colleague at ETH. And so it's a collaboration. The key thing is that we essentially, for example, from the RGB frames, we can now we learn to predict the depth, but also the gaze, and the camera trajectory, and all those things are essentially can be cross-predicted. So this is really a model for kind of, and for egocentric actions, really kind of quite powerful there, quite useful. Okay, so now more towards robotics. So here, and people and robots working together and building digital twins for this. So here, essentially, what you see is a scene graph representation that we've built up for this scene. And then you have a person carrying out a task, and that changes. So we keep track of how the scene graph changes. This can also keep track of if an object gets put into another object, for example, and it's hidden from view, but we know it's been inside because we've observed that action of putting it inside. And then that's available, for example, for the robot to later go pick up the object or things like this, as you could see in this. We've also started doing a lot of work towards explicitly finding affordances. So this is a data set that was published at CVPR last year, where we've annotated in these models. So not only the semantics, that there's a hook there, or so but essentially what action you're supposed to take there, a hook pull, have the geometry of this described through the hinges or through the direction on which you're supposed to press or rotate or whatever. And also then the description of what the action will actually accomplish. And then here's some work on the robotic space, where we've essentially, we build up first a kind of a scene graph representation, but now we want to add some of this functionality to it that we would observe. So we would detect the switches. So we learn to detect the switches. We've actually built a whole data set for that. So we build this scene graph. We identify that there's lamps and switches, but we don't know which lamp, actuates which switch actuates which lamp. And so we have the robot essentially go and explore the space. And so it goes, presses a switch, and then goes checking which of the lamps are switched on with this switch. And that allows us then to update the scene graph and put a functional relationship between that switch and that lamp. Right? And so now, what you see also, we know roughly where the switch is from the initial mapping. And then whenever we go there, we do a refinement to actually press precisely, right? Because so that we don't have to do it open loop. We go close to the switch, redetect the switch, and then press the switch, for example. This is actually our switch data set. If somebody's interested, we have lots of data collected there. And here's kind of just Spot kind of manipulating some of those. Then our next work, this is a collaboration with Stefan Leutenegger and his team, who used to be at TUM, but is now actually moved also to ETH. So this is work where we're essentially looking at egocentric data. This was mostly done on Ego 4D. So we record all of these actions, we process them, and we extract, like when I open the fridge, like if I see the switch, this is the motion that I'm doing with my hand to open the fridge. So we essentially learn to predict from the kind of the grip of the fridge, like what is the motion that should be done by was done by the person, and therefore we want to have the robot execute. And with the idea that this is a representation that we can also leverage cross-modality, across embodiment. As you see here, so this is Stretch executing some of the actions. So essentially what happens is we're looking at the scene, we're seeing like what action we might take, we predict the motion that should be carried out, so the grasping and pulling motion. And so notice opening a cabinet means you have a rotational motion, which is while others have a pull motion only, et cetera, et cetera. And you see here kind of cross embodiment, kind of deployment of these policies. Here are some more tasks here. So let me get quickly through that. Here, see some of the light switches and stuff. Okay, picking objects. Then Liz work, which is that we done in that space that's not yet published, is essentially to also here we observe from Ego4D, we observe how people are grasping. In particular, we observe the two grasping points that people are doing. And then we're essentially rolling back the video. So essentially we learn to predict from before we grasp to where the grasp should happen. Okay. So let me just show that. So we predict the grasp points, and then we use that to deploy that to robots and generate grasp trajectories based on that. So here's just a few examples of that. And we do this with hands. And so we predict where the thumb and where the other fingers should grasp based on the kind of seeing the scene and then using the prediction. This works quite well. And then just to wrap up some of the ongoing work on building digital twins we have a physical lab space. We've built a full digital twin for it. We do randomization to train the policies. That was like, this is just ongoing like these days. So this is some ongoing work. Also lots of data collection efforts going on. In particular, this one that has, IKEA-style furniture, where we collected many hundreds of interactions. We have 235 articulated parts in the things we've observed. And we've collected both humans interacting with it, then humans kind of essentially using a gripper as the robot has, and then the robot grasp also. We collected all of those different ones, collecting data there from different viewpoints, because you both have the different robots will have different ways to interact with the scene, etc. So that's ongoing work that you can look forward to see more about, and I'll wrap it up here then.
I'll take a while to look my test, so I'll have to. Construction part. So I was wondering if we for our street or system people things. Do you think images and videos are using images and videos all going to be eventually sufficient? We still additional features like providers or regulators, so sometimes more expensive to acquire for activity.
I think like city scale reconstruction can be done just from images if we have the data. Especially, I mean, it depends how you collect the data, but if you collect the data, if you want to do it from a photo collection, it's going to be difficult because it's the distribution is not good, the coverage is not good, and so on. But if you have data that's structured, that's been collected in video streams that cover everything and so on, there's really no problem. To do that. Actually, it was done, like I think we reconstruct the whole of San Francisco, like more than a decade ago, for some data sets. In particular for city scale or things like that, in most scenarios, you actually have GPS available anyways to give you coarse localization, which simplifies lots of things. You know what could match what. So you don't have to, match at like the full quadratic scale. You can only match things that are nearby, so that reduces that cost. And some of the ambiguity and so on. And so if you have dense enough continuous coverage, essentially, of having, images every few meters, kind of in a structured way, and you know which ones are taken in sequence, and you have GPS to help you, there's not really a problem to do those things. There's problems, there's like a lot of still open problems to avoid some issues, but scaling it up to that is not in itself a problem. Yeah.
For robotic annotation, so people use VLS today.
Mm-hmm.
Have directed from images to actions without any explicit tuning. They think that is the future, can be improved things. I
mean, that last one is essentially a VLA. We provide that additional info, so we make it predict that additional that information of the grasp. Like we feed it that information and we make it predict that because we've seen that that helps it kind of do better. But it's essentially a VLA. I think the jury is still a bit out. I think there's lots of challenges with the speed of that you can run those things at. You want a model that's very general that can. So I think there's still many challenges that are open in that space, but I think it's very interesting. We'll see if that's the kind of the final thing or not. But there's certainly a lot of people betting on those at this point. I think there's a lot of interesting things that you can do with it. I think we still have also many challenges to solve to really deploy those things. They're not very effective in a kind of fast control kind of setting and so on. But I think it's a very exciting direction. So we're certainly looking into that.